received an email with your grade, right? A report. And it was sent either to your Olympic College email or to the email that you use to register with WebAssign. If you can't find it, you can tell me about it and I'll tell you what email I used. And if that one's not available to you anymore, I'll change it so that, and I'll resend it and you can get it that way. So we are going to start chapter 8 today. We're going to look at introduction to random variables. And in particular, we're going to be focusing on what's called a probability distribution. Sometimes they add the word table, most of the times they don't. So a probability distribution table is a table that contains all the events that could happen and their probability. So let's suppose that we have can't think of that now. Yeah. We'll have the number in the family. So you collected some data and there was single child, you and a brother and sister, that one and that one. And that's all there was, right? In my sample, you either were an only child or there was 4 in your family, right? And we collected a sample, say, and 0.3 had 1 single, 0.4, 0.15, 0.15. And this is the probability. So the chances that you choose a single person and they come from a family of 3 is 0.15. And probability they come from a family of 2 is 0.4. Now, one of the things that has to be true about a probability distribution is, what do you think these 4 probabilities should always add up to?
1.
And if they don't, you've made a mistake, right? That's bottom line, right? They must add up to 1. I've got a little weird background sound, so I'm going to mute you. So if you remember, hit spacebar, you want to answer. Right, let's continue. So the first couple of questions that they give you are very simple. I think they are. I hope you agree. Where they give you a probability distribution, and I'll just call it X because I'm lazy. And the probability that you get X. So X could be 1, 2, 3, or 4. So it's basically that. This is 0.12. This is 0.3. This is 0.45. And all you have to do is to fill in 1 missing probability. Are we good? Anybody tell me what to do, even if you can't do the calculation in your head? How would I find that last probability? I know these 3 and I need to know what that one is.
Add the previous 2 probabilities together and then subtract them from 1.
Okay, so if you add them all together, you get 0.87. You take that away from 1, you get 0.13. Are you comfortable about how that worked out? That makes sense? If you tell me 3, can't I figure out what the last one has to be? Because all 4 add up to 1. So you add these 3 up, 0.87, take it away from 1, whatever's left is your answer. Now, probability distributions are very often given, the probabilities are given as decimal, but there is no reason why you can't get them as fractions. So here is, we'll just do X again, so we don't need to worry too much about. Let's say it's 5, it's 10, it's 15, it's 20. And I tell you that this is a third, that this is a quarter, and just to be different, this is a fifth. Don't you tell me the answer, but the probabilities here are all in the form of fractions, right? Which can happen as well. Again, how would I find the answer? Don't need to know the answer, but how would I find it?
You would add the fractions and then subtract them from 1.
So if you wanted to see it as a calculation, isn't that the adding? And isn't that taking it away from 1? So if I go to my calculator, I hopefully should be able to do that. 1, take away, put a bracket around it. 1/3 plus 1/4 plus 1/5. And somebody was asking me during the test, how do you turn things into fractions? Here it goes. Math button, number 1, enter. And the answer is 13/60. Are you comfortable with that type of question where they give you a probability distribution table, they fill in most of it, but they leave one of them blank, and your job is to find out what that would be. If it's a fraction, they want fractions as an answer. And if it's decimals, right, they want a decimal for your answer. And that basically is just question 1 and 2. So far, so good? Right. Now, the next question I'm going to deal with is question 3. Going to take me a few minutes to set it up, and I want to actually draw it so I can point at things and so on. So this is some data that was collected from a hospital, and these are the number of births, deliveries in a given, what was it? Yeah, so 0 births, there was 1 birth, 2 births, one of these were 3, 4, 5, 6, wow, and 7 births, and they're calling that variable X, and then they have the probability. So you can imagine over a long time period, they've collected data on how often a birth happens. Well, on 0.09, so that's a percentage chance that on any given day, no kids are born, right? And then 0.12, 0.24, 18, 0.06, 0.02, I'm out of sync here, 0.06, 0.12, 0.24. There it is. 0.28, 0.18, 0.06, 0.02, and finally 0.01. Now, if you worked for a large hospital and you were in the maternity ward, for instance, wouldn't data like this be quite useful for staffing? You know, how many nurses do we need? Well, would you agree that the typical answer is 3 births in a day, right? And doesn't that happen about a quarter of the time, a little bit more than a quarter of the time? Now, some days, right, what's that, about 9% of the time, nobody's going to be born. And, you know, extreme case, you know, 1% of the time, there might be 7 births on any given day. So the first question is a notation issue, and it's written like this. X represents the number of births. So if you wanted to kind of write this out a little bit more English, Aren't they asking us what's the probability that the number of births on a given day is less than or equal to 3? Now, when you go to this table, less than or equal to 3, right? That means you could be 3 or less, right? That's another way of saying it. And isn't it those 4 events? What do you think you do to these 4 decimals that would give you the probability that the number of births is less than or equal to 3? What'd you do with these 4 guys?
Multiply them.
If you didn't multiply them, what would be your second thought? This, and then this, and this, and then that. How might you do with these numbers? Any suggestions?
Would you multiply them all?
No, I got that earlier. I kind of think what's happening here is that you're thinking, not surprisingly, you know, when 2 things happen, don't you multiply them together? And when 3 things happen, you multiply them. And that is true in the questions where you're doing something and then you're doing something again. But here, it's only one event, right? And the one event is that the number of births is less than or equal to 3. So you just add these guys together, right? So I should be able to do that. It's 52, 62, 79. So about 79% of the time, you are going to have 3 or less births. So if you're looking at how many doctors, you know, maternity doctors, I'm not sure what the right name is, but you know, the doctors that help give birth, how many do you need? Well, you could say, look, if one doctor can handle 3, 80% of the time, we're going to be good on one doctor, and we only need a backup, you know, the other 20% of the time. So it stops you having a hospital with a lot of doctors waiting for people to have babies when those doctors could be, you know, somewhere else doing.
I got
I don't know.
0.73.
Yeah, me too.
Is that because I can't count? Yes, that would be the reason. Let's go on and do another one of those table ones. In question 4, well, actually I could do this one. It's probably quicker if I just do this one on the screen. Yeah. So we're going to create a probability distribution table, right? And we're going to do it from a story involving throwing coins. So I've lost the damn question. Here it is here. For a fair coin tossed 3 times, there are 8 possible events. And here the 8 of them are, right? See them all there. Let X be the number of tails. And let's see if we can find the probability of each one of these events happening. So I'm going to pick one at random. What's the probability that you get 2 tails? Well, I know there are 8 things. So don't I need to just figure out how many of those 8 things are exactly 2 tails happening? Because then maybe can I make this bigger? A second to come back to that question. Maybe make it a touch bigger. Here we go. 1, 2. Right. How many of those 8 times do you get 2 tails? Exactly 2 tails. Just a matter of count. Let me see. There's 1, right? That one there. That one there. And that one there. I only make it 3 unless I miscounted. Does that look like 3?
You missed
3
one
out
at the end, the 3 tails.
but I said exactly 2
Oh.
tails. So you're not
Oh,
allowed 3. Yeah. But if it was 2 or more, that'd be different, right? How about getting 1 tail? How many out of the 8 would that be? Exactly 1 tail.
2.
Okay, I see one of them there. I see a second one there. I see a third one. You agree all of them are one tail?
Yeah, I
You're
overlooked the
missing them.
first one. I didn't see the first one. Sorry.
No, you shouldn't be sorry. I missed more than you do. Let's pick that one because it's easier to understand. Out of those 8, how many of those 8, so that's going to be the probability of it happening, are 3 tails?
1.
Just one. Now, I can tell you what that answer has to be. Doesn't it have to be 1/8 because the whole thing has added up to 1? But isn't 0 tails mean you got 3 heads? So there's only one of them. And that's it. That's what that one looks like. Right? Now in question 5, here is a random, a table, right? A probability distribution table. And it's giving you X the sum of 2 values. So they're rolling something, whatever it is. The probability that the sum is a 4 is 3/9. The probability that the sum of them is 6 is 1/9. It says here, what is the probability that the sum is even? So if you look at where evens are, that's even, that's 1/9. That's even, that's 3/9. And that's even, that's 1/9. So if you notice that in these tables, you add things together, right? So what's the probability of you getting even? 1/9 plus 3/9 plus 1 more 9. And I hope that's 5/9. Are we good with that? Actually, we're almost finished. There's only 8 questions. It's a very short intro. Now, the next group of questions, I think I should probably write these down and do it on paper. So a kindergarten has 6 left-handed. Okay. And 16, oops, I'll write that down in his numbers then. So if you're left-handed, 6 of them. And if you're right-handed, it's 16. And 2 children are selected at random without replacement. I should show you me writing this down as well. That would help. So we're going to take all this information and we are eventually going to construct a probability distribution table, but it's a little bit messy. So 2 children chosen at random. And the key here is without replacement. And we're being asked to find these events, that the first child and the second child were both right-handed, that the first child was right-handed and the second was left, that the first one was left and then the second child that you chose was right-handed, and lastly, that the first and the second child were all left-handed. Remember that story with the bag of beads and some were red and some were green? This is essentially the same kind of story. Now, if you want to find the probability that the first is right-handed and the second is right-handed, this is a situation where you multiply, right? Now, since it's without replacement, that's important. There are 16 out of a grand total of 22 kids here, right? So the chance that you pick a right-handed child first time out is 16 out of 22. Are we comfortable with that? Now, the first child is right-handed. There's only 21 kids left, right? How many of them are right-handed?
15.
And that's the guy that represents that probability. Now, if they'd done with replacement, wouldn't it be 16 over 22 times 16 over 22, right? The thing wouldn't change. But without replacement, the numbers change. So I'm doing that in my calculator right now. 16 divided by 22 times 15 divided by 21. And, oh, make it a fraction. 40 out of 77. Now, if you do a right-handed, it's 16 out of 22 again. Now there's only 21 kids, but the second child needs to be left-handed. So do you see that 6? Right, 6 out of the 21 for the second part. Right, first one right-handed, second one left-handed. It's going to take a few moments to do that as well. 16 out of 22 times 6 out of 21. And you get 16 out of 77. These two are very similar, but it's a left-handed kid the first time, so 6 out of 22. There's 21 kids left, and we want to know what's the chance that you get a right-handed one amongst them, and that's that guy. So back to calculator. 6 out of 21 times 16 out of, I just said 21, didn't I? Let's go back and fix that. 22. And then 16 out of 21. And the answer, when you turn into a fraction, is 16 out of 77. Now, I'm going to do this question, but I'm also going to figure out a way of checking that I did these three right. If you add up these three and take it away from 1, shouldn't it be this answer? So I'm going to add all these guys up and take them away from 1. So here we go. 1, take away, put a bracket around it, and then just put those 3 guys in. And the answer I got is 5/77. Right. Now I'm going to do this guy. You know, the same way as I did the other 3. And if I get 5 out of 77, I'm going to go, great, I must have done it right. If it doesn't match, doesn't that mean, not that I've ever done it, that I screwed up in one of my calculations? So there are 22 kids, 6 are left-handed. Check. You've used that child up, so now there's only 21 kids to pick from, and there's only 5 of them who are also left-handed. So we're now going to be doing 6, 22 times 5, 21, and make that a fraction. And isn't it good when things come out exactly the way you should have? 5, you see it, 5/77. And then you are being asked in part B. So all of this was part A. Part B was the probability distribution. And this guy here is going to be number of left-handed. And they're just calling this guy K this time because they wanted to. And then Px equals K is just another way of saying probability. And you could have got none, you could have a 1, or you could have a 2. Oh, that's a very small table. There are 4 events here, right? 2 right, right left, left right, left left. How many of these is both left-handed? 2 left-handed kids. Which one of these probabilities is 2 left-handed?
5/77.
I agree. Now, if you want to do 1 left-handed, isn't 1 left-handed actually 2 separate events? Right?
You add 16/77 plus 16.
You nailed it. You're on top of it. Now, if you wanted to do 0 left-handed, isn't that just another funny way of saying 2 right-handed? Or couldn't you just add these and see what's left from 1? But both ways work. And now you've created a probability distribution tree, table, I should say. If you look at these guys for a minute, just superficially, but I think it makes sense. Isn't the most likely thing to happen that you pick 2 right-handed kids? Wouldn't that happen more than half the time? Could you pick 2 left-handed kids? Yes, but that would be about 8% of the time. Wouldn't you be kind of suspicious? Well, maybe not suspicious, but oh, that's a weird coincidence, right? It wouldn't happen that often.
What's the table called?
These tables are all called probability distribution tables. Every single one of them. Now, the next story is a pain in the butt, but it's a good question. But you're going to have your thinking cap on, and I'm going to try and make it as clear as I can, because it is a bit like fog. What we're doing here is a woman has this is the story. A woman has decided to have children until she gets her first boy, or until she has 4 children. My sister Morag wanted the other. She wanted a girl, and she gave up at 4, right? But in this case, she wants a boy. The minute she gets a boy, her family's finished, right? She's not going to have any more kids. And she's going to keep trying to have that boy until she reaches 4th child. If she gets to the 4th child and she hasn't had a boy, right? She's just saying, that's it, I'm not going to try anymore. So X is going to be the number of children that she has. Right? Did she get it in the first child? So 1 child. Does she need 4 kids? Right? They then even tell you, thankfully, what the events could be. Wouldn't that be the first child as a boy? She stops. Couldn't she have a girl and then the second child as a boy? So she stops. Couldn't she have 2 girls and then she gets a boy and stops? Couldn't she have 3 girls and then the 4th one was a boy and she goes, thank goodness for that, and she stops? There's one more event. They gave it to you, but does anyone want to predict what the last event would be? Because there's one more situation.
4 girls.
Yeah. Now, in this world, the probability of getting a boy is 0.5, because they tell me. And so won't the probability of a girl also be 0.5? Right. So if that was 0.52, wouldn't this be 0.48, for instance, right? They add up to 1. So they've told me that. And now they ask us to find a whole load of probabilities of each of these events. So let's find the first one. The probability of getting a boy is simply just 0.5. Don't overthink it. That's what it is. Now, the probability you get a girl and then a boy. We will make the assumption that this is with replacement. I know that sounds a funny way of saying it, but would you agree having a boy and then getting another boy or girl? We're keeping them the same, right? So nothing changes, right? Probabilities do not change here. So won't this be just the probability that you get a girl multiplied by the probability that you get a boy? In this case, I wish these numbers were different, but in this case, you end up with 0.25. Okay. And then you have the probability of 2 girls and a boy, which is basically a girl times another girl, and finishing with a boy. Can I cut some corners here and say it's just going to be 0.5 cubed? Right. I think that's 125, but I'm not taking any chances. So let me find out. I was right. Gotta put circles around my answers. I'll start losing track of them all. There they are. There they are. That's that one. 2 more to go. You could have 3 girls and a boy. So that would be a girl, yet another girl, and finally a boy. And to cut some corners, since everybody is 0.5, you get that one, and 0.0625. Again, I'm taking no chances. Wow, I'm on a roll, that's right. Circle around it. One last one to do. And that's just everybody was a girl. So you want to find the probability that you get 4 girls in a row. It ends up also being 0.5 to the power of 4, and it ends up being 0.0625. And that's question A finished. Are you still with me, guys? Now we're going to create a probability distribution table. And K is going to be number of children in the family. And then underneath, they're doing that P x equals K, which is just short for probability. Now you can have 1 child in this story, 2 children in the family, 3 children in the family, and 4, because right, she stops on 4. I don't need to go further. Now, what happens if she's only going to have 1 children in the family? Does it not mean it's this guy here? So 0.5. What is the probability that she stops with 2 children in her family? Two children in our family.
0.25.
This one here. Agreed. What about 3 children?
0.125.
Okay. Now, the last one is 4 children in the family. And that definitely means 4 children in the family, but doesn't that also mean there was 4 children in the family, right? For 2
Does that
different
mean
reasons.
we add them?
Yeah, it does. It means exactly that. And if you add them, you get 0.125. But of course, if you were stuck on that last one, couldn't you add the 3 that you know and take away from 1 and you'd still get the answer, right? So you had a backup plan, right? If you're doing a probability tree and there's 1 left and you're really not 100% sure how to do it, shouldn't it be add up everybody you do know and take away from 1, and that's what it has to be, even if you're not sure, you know, why it's what it is. Are we good? Cool. That's it. We are finished. I said 8, there's only 7. I was mistaken. That is us finished the first one of these 2 sections. Chapter 8's quite a short section. Actually, it's a very short section. So now we're going to do chapter 8. The normal distribution. And there's going to be a fair amount of overlap and then some new stuff. If the mean of a test was 72 and the standard deviation of the test was 10, right? Suppose I told you that. And this is hopefully stuff you've seen before. And John got 83 in this test. One of the things that we like to calculate is what's called the Z-score. You remember that? We actually had questions in the test because we've done Z-scores before. Can anyone remember the formula for calculating the Z-score? In this case for John.
Score minus mean divided by the standard deviation.
You nailed it. You nailed it. Scored. I've written down the symbols, but if you want it in English, it's the score the person got, take away the mean of the situation, divided by the standard deviation. So in this case, he got 83, the mean was 72, and the standard deviation was 10, and I believe that comes out as 1.1. Are you comfortable? Do you remember doing these guys? Z-scores. Could be asked a question, is John's score an outlier? I know his Z-score is
Yes.
1.1. Think carefully. How big a Z-score do you need to be an outlier?
Is it 3?
It is. So that's the guy you remember. So is this guy, now that we've mentioned that, an outlier? Z-score is 1.1. Was John an outlier? No. Isn't his Z-score? It's not bigger than 3. Also, because it could happen, can also be less than -3, because you could be an outlier because you're really, really small. Okay. Do another one. Let's suppose in a particular place during the summer, the mean temperature was 91 degrees, and over the last whatever 100 years, the standard deviation was 5 degrees. And last summer, right, the temperature, so that's like the score, was 99 degrees. And our question is this an outlier? Well, to do that, you find the Z-score. So in this case, it's going to be temperature, take away the mean, divided by the standard deviation. And I believe you get the answer, 1.6. So getting a summer temperature of 99 degrees, is that an exceptionally hot? Is it an outlier, in other words, for this particular place?
No.
No. It's my last one of these. Janice has an IQ score of 157. The mean of IQs is 100, and the standard deviation is 10. Is Janice an outlier? Is she got an exceptionally high IQ? Let's find her Z-score. 157, take away the mean, divided by 10. And she has an IQ score of about 5.7. Is she an outlier?
Yeah.
Yeah. An outlier must have a score greater than 3. 5.7 is definitely greater than 3. In fact, if you wanted to know, and we'll be doing questions like this, how rare is getting an IQ of 157? Well, it's more than 3 standard deviations away, which already puts her in the top 0.5%. She's probably a 1 in a million, right? Like 300 Americans have probably got that kind of IQ score. That's how exceptional that would be. So if I give you the mean, the standard deviation, and a score, are you comfortable about getting the Z-scores? Are you also comfortable about yes, it's an outlier or no, it's not, if they tag that question up? You're all good? Right, I'm just going to pick one question from the homework just to kind of show you how they would phrase it. So it's good to kind of see what it looks like. So loading it up as we speak. Stop share, and you're going to see some notation. I think I hit the wrong one. Let me try that again. Go away. Try that a second time. Here it goes. Oh, I think I was right the first time. Are you looking at question 1 with salt? Now, notation is always interesting because sometimes they change the notation on us. Here, the mean is 0. They're using that Greek letter mu. Can you remember what the Greek letter mu is the mean and what x bar is the mean? Because they're both mean, but what's mu mean? It's the mean of population. Right? That's all it means. So treat it like x bar. It's no different. It's just a version of x bar. And the standard deviation is sigma. We tend to use those when we are doing populations as they are. So the z-score here would be 1.3, the score, put a little bracket around it, 1.3, take away 0, and divided by 1. In fact, that is such an easy calculation, I'm just going to do it. That's your answer. Now, if the mean is 18 and the standard deviation is 7, and the thing they're calling value x, think of that as the score, then in this case it would be 4, take away 18, and then divided by 7. Now, if you're doing that in your calculator, it's a good idea to put those brackets in. So I'm doing it right now, bracket, 4, take away 18, close the brackets, divided by 7, and the answer I get is -2. Are you comfortable about the way that they ask you to get z-scores, right? The mean is going to be called mu, and the standard deviation is going to be that little funny sigma sum. Basically, more of the same. And this would be a good point for me to finish. When we come in tomorrow, we're going to show you how to use these salt buttons. In particular, what we're going to do is find out things like how exceptional that girl with an IQ of 157 is. And we're going to use salt to do that. And that's going to make it quite easy because salt does all the heavy lifting. You just put the numbers where they need to go and boom, the answer you want will pop out at the bottom, and that's all you write down. Perfect.